All right, folks, so we'll work here with a nice warm-up. We're just going to sketch our function f at x is equal to the cosine of x. Now, I know we sketched this function as a part of our lesson yesterday, but I encourage you to do right here, because you will be using this function for many years, I encourage you to pause the video here and do your best sketch of this function, and then unpause the video and compare your work to ours right here. All right, at this point, I will start sketching mine. Okay, so f at x is equal to the cosine of x. Well, what I know about this function is its maximum is positive 1 and its minimum is negative 1. I know that its period is 360 degrees. So that's right here. So I know half of its period is 180 degrees. Half of this space from 0 to 180 degrees is 90 degrees. And half of this space from 180 degrees to 360 degrees is 270 degrees. Now, when I'm graphing my function, then I know as a cosine function, it starts at its maximum, and then it goes to the middle, it goes to its minimum. Then it goes to the middle again, and back to the maximum. So my general shape, a nice, smooth, calm cosine curve, looks something like this. Right here. Now the function continues in both directions. It continues with this pattern, so we'll need to make sure we sketch it with our arrows. Now, okay, we've plotted our cosine function. Now we want to consider, if this was a sine function, how could we transform a sine function so that it matches up with this same shape? Well, I know a sine function, let's look down here. A sine function, the general shape would look like this. It's the same shape, but in a different location as we discussed yesterday. So my sine function would look like this. So, all right, well, I'm going to need an amplitude, a period, a phase shift, and an axis of symmetry. Already, my base sine function shares the same amplitude, it shares the same period, and it shares the same axis of symmetry as that cosine function that we already sketched. So my amplitude is going to be 1. My period is going to be 360 degrees. My axis of symmetry is going to be, where y equals 0. And then all I need is my phase shift. So my phase shift, I can accomplish this by translating this function horizontally over. How many degrees is that I've translated it over here? Well, that's the same as this degrees right here. So from 180 degrees to 90 degrees. So my phase shift is 90 degrees to the left. Fantastic. Now, if you're able to follow that, fantastic. We're off in a good direction. Now we'll look at example 1. So we're going to practice here, this entire note, we're going to practice coming up with transformations on these base functions to match a certain set of characteristics. So if we consider a sinusoidal function that has these characteristics, A, P, the phase shift, and its axis of symmetry. We want to determine which transformations a base function must undergo to come up with these characteristics. So let's take a look. Now, we don't even need to determine, in this case, if we're working with sine or cosine, because all we're told are these characteristics. So I know my amplitude. If I'm working with sine or cosine, I know my amplitude is going to be 1. If I'm working with sine or cosine, I know my period is going to be 360 degrees. My phase shift is 0, assuming it's my base function, and that's what I'm working with here, my base function. Then my phase shift will be 0, and my axis of symmetry is going to be y equals 0. Fantastic. Now I need to transform. I need to figure out which transformations can bring me an amplitude of 3, a period of 60 degrees, a phase shift 45 degrees to the left, and an axis of symmetry y equals 1.5. We already discussed yesterday which transformations go along with which characteristics. So if I'm looking at my amplitude, I know my amplitude is the distance from my axis of symmetry all the way up to my maximum. And that's going to be the same as the distance from my axis of symmetry down to my minimum. Well, I can change my amplitude by adjusting my vertical stretch or compression. So if I need the amplitude 3, then I would need to multiply this amplitude by 3 to get there. So I would have a vertical And you know what? I'll change my color here because we're used to working with a nice light blue with our amplitudes. We would have a vertical stretch because it's increasing in size. Vertical stretch by a factor of 3. And I'll just move this over to give ourselves a little bit more space right here. Of 3. Fantastic. Okay, then my period. All right, well, my period was originally 360 degrees, and now it's 60 degrees. So what did I multiply 360 by to get to 60 degrees? Well, I'll need to divide it, right, because it's a smaller number, or rather I'll multiply it by a fraction. Now 60 degrees, if I think about that, okay, 60 degrees times 1 is 120 degrees, times 2 is 180 degrees, times 3 is 240 degrees, times 4 is 300 degrees, and times 5 is, you know what, where did I make a mistake in here? There we are. Let's fix that. I made my mistake right at the beginning. 60 degrees times 2 is 120 degrees, times 3 is 180, times 4 is 240, times 5 is 300, times 6 is 360 degrees. So if that's the case, then I am working, and I know my period is getting lower, it's getting smaller, so I have a horizontal compression, and it's going to be a horizontal compression by a factor of 1/6, because I would have needed to multiply this new period by 6 in order to get that original period. Fantastic. And if you feel a little confused there, feel free to rewind the video and watch it again. All right, so we have a horizontal compression by a factor of 1/6. Fantastic. Now our phase shift, this is the easy one. They tell us that our phase shift is 45 degrees to the right. That means that the horizontal translation is exactly the same. Horizontal translation, 45 degrees to the, to the left. I think I said right before. And lastly, my axis of symmetry. So my axis of symmetry comes from my vertical translation, right? If I pick up my function here and I move it up or I move it down, then my axis of symmetry moves up or down with me. So if my axis of symmetry was originally 0 and it needs to be, 1.5, then we can simply add 1.5 to our axis of symmetry. So we have here a vertical translation, 1.5 units up. Now I encourage you right here, and I can do this on the uploaded version, or actually rather you could, I'll do that. I'll include this on the uploaded version. I encourage you, pause the video here and practice sketching this. We should be able to sketch a function with these characteristics. We practiced that in yesterday's lesson. So pause the video, try it out. Once you're finished, then you can check your answer with what's uploaded. We're going to move on in the video here, though, to example 2. Example 2, we want to determine which transformations this sine function has undergone, because we know our original sine function has an amplitude equal to 1, a period at 360 degrees. It has no phase shift, and we know that it has an axis of symmetry at y equals 0. So we need to come up with the new characteristics, and then we can go through exactly the same process that we went through up here to determine what kind of transformations could have gotten us there. So I encourage you, actually, again, you should be able to handle this right now. I encourage you to pause the video and come up with the new characteristics, the characteristics that this function has undergone. We know it's a sine function. They tell us that. So we know its base was y equals the sine of x. Try it out. Again, pause the video here, go for it, and then unpause, and you can come back and see how you did. And what do we have here? Our phase shift and our axis of symmetry. Fantastic. So, we already discussed yesterday, we practiced this, you might find it easiest to start off with your axis of symmetry. So, if I look at this function, all right, well, I know the maximum here is at negative 0.5. I know the minimum here is at negative 1.5. Halfway between those is going to be my axis of symmetry. So you could add those up, divide them by 2. My axis of symmetry is negative 0. Oops. Let's fix this. That's y equals negative 0.5 plus negative 1.5. So I'm adding them up, dividing by 2. Negative 0.5 plus negative 1.5, that is negative 2 divided by 2. Okay, so my axis of symmetry is at negative 1. That is halfway exactly between my maximum and my minimum. Good job, us. All right, now that we have our axis of symmetry, our maximum and minimum, or minimum, could be used to determine our amplitude. Now, we can just find the distance. Okay, what's the distance between negative 1 and negative 0.5? That's nice and easy, nice and straightforward. We're working with an amplitude at 0.5. All right, our period. For the period, we need to find a couple of points in here that are exactly one period apart. We don't necessarily need to start at the beginning of our sine shape, because that might not give us a perfectly clean degrees. But right here, I can find a perfectly clean degrees because I'm given two of these points, negative 900 and 180. And these are in degrees, by the way. So that means one period is the distance from negative 900 to positive 180. We can find that by working with 180 degrees plus 900 degrees, or rather minus negative 900. Let's show that in here. Minus, because it's a difference, negative 900 degrees. And this is equal to 1080 degrees. Lovely. So that's our period. Wow, our period's way bigger this time. That's okay. And our phase shift, we would need to determine, okay, how many degrees has this been transformed, either to the left or to the right? Well, this one's a little bit trickier because I might see this spot right here. This is normally the beginning of my sine function. The problem is I'm not exactly sure how many degrees this is moved over from my origin. So I can check with a different value. You know what? No, we can't. That's going to be a little bit more complicated. So what we're going to do here is just estimate. All right, so I know it's slightly less than 100 degrees to the left. We can guess that that might be 90 degrees to the left. So we'll estimate this is 90 degrees to the left. Awesome stuff. If you have a question like this on an assessment, I'll make sure the lines or the points specifically are given to you so that you can figure it out without so much guesswork. All right, so if we're going through this problem, we need to ask ourselves, what happened? What kind of a transformation makes the amplitude go from 1 unit to 0.5 units? Well, that's nice and simple. And you know what? I'll encourage you to pause the video here and try it out. Try and come up with these transformations, just like we did in example 1, and see if you get them right. But we're going to work through. Okay, so we're going to have a vertical compression because it's getting smaller by a factor of 1 over 2, because I have to multiply 1 times 1 over 2 to get to 0.5. Good, then I look at my period. And this one, like we said before, it's getting a little more complicated, but I can see my period was 360 degrees, now it's 1080 degrees. That's a period that increases in size, so we have a horizontal stretch, not a compression, but a stretch here, by a factor of, and then we have to check, okay, well, 360 degrees times 2 is 720 degrees. Times 3, that's when we're going to get to 180 degrees. If you're not sure on that, well, let's head over here. 360 degrees plus 360 degrees, okay, well, that's going to be equal to 0, 12, 720 degrees. Okay, and then let's add another 360 degrees right here. 0, 8, 3, and 7, that's 10, 1080 degrees. You should be able to handle a problem like this without a calculator. So I know that it's horizontally stretched by a factor of 3 because I added 360 degrees once, twice, 3 times. That's the same as multiplying by 3. And then if we have, again, this is the simplest one. We have a horizontal translation because that's the same as a phase shift. Translation, 90 degrees to the left. And our axis of symmetry. So our axis of symmetry was 0 for our base function, and now it becomes -1. So it's been picked up and translated. How many units has it been translated? It's been vertically translated. Translation, 1 unit down. All right, nice work. Now lastly, we're going to go over, and this is, you know what, this is the exact same example as last time, so we're going to have to change it up. Rather than sketching a cosine function that has these transformations, we want to determine the characteristics. Characteristics of this function. So it's been vertically stretched by a factor of 2. Again, we know our original characteristics. We have an amplitude of 1. We have a period that is 360 degrees in length. We have no phase shift. And we have an axis of symmetry at y equals 0. Well, now this has been vertically stretched by a factor of 2. And if that's the case, our amplitude that was originally 1, our amplitude becomes 1 times 2, and that's equal to 2. All right, our period was 360 degrees. Now it's being horizontally compressed by a factor. Oh my goodness, this is, let's get a little bit, I'm hoping you folks can be patient with Mr. Pasatka here. Horizontally compressed by a factor of 1/3 because it's compressed, so this value needs to be less than 1. Horizontally compressed by a factor of 1/3, that means our period was 360 degrees, and now it needs to be multiplied by 1/3, so I'm working with 360 degrees divided by 3, that's 120 degrees. Our phase shift. All right, well, it's horizontally translated 30 degrees to the right, so nice and straightforward. That means we have a 30-degree phase shift to the right. And lastly, if it's vertically translated 1 unit up, then we're going to have an axis of symmetry. It was at y equals 0. It's been picked up and moved 1 unit up, so now we have our axis of symmetry at y equals 1. Again, I might encourage you folks, do your best. Try and sketch a function that has these characteristics. Like I said, the uploaded version will have those answers. Nice work here, folks. You should be able to handle the questions from 5.4 now.